Yeah, we should start now.
Hi. Um, Good evening, all of you. This is like probably as of now the last session for this term because everybody are going to be busy with quizzes probably, unless you guys ask for something else which is needed. Um, so here we are with the second part of hypothesis testing. Like test the truth was the name of our program. So we are continuing with the lecture session. We should name it probably like just introducing you to the concepts of statistics which are more useful and relevant to you, or which are very basic to statistics and you would find interesting to go ahead with. Okay, so hypothesis testing, as you had, welcome all of you and thank you for joining. Sorry. Okay, so hypothesis testing, if you could actually recall from the previous session, what we did was we are trying to see if our claims on a particular population parameter are valid or not. And in general, we discussed there are parametric and non-parametric tests, and we just said what are the two types of errors, the type 1 and type 2 error, with which we actually determine how to move forward with our hypothesis testing. And then we also checked what's a null and an alternative hypothesis. And always our testing happens on the basis of your null hypothesis, either with the evidence that you have, you reject your null hypothesis, or you do not reject your null hypothesis. That is how we formally go about. Now this is just a continuation, like the same introduction that we conducted. You do a testing. Okay, the testing is based is done so as to reach upon a conclusion, right? To reach upon some decision based on some samples that we have actually taken up. Now, if you could actually find out if your data is supposedly following a few assumptions that the test require, and the test that we are conducting is stemmed out of some distribution, already known standard distribution, known sampling distributions, then you could say that we are performing a parametric test. Now, the other coin is, your data is not satisfying any of the ends. Okay, your data is not satisfying the assumptions of your assumptions that are required to fit into those sampling distributions. Then you go into non-parametric test. Now I would be handling the parametric test part, and the next person, and there is something called ANOVA. When you actually go into the, you are analyzing the variance of different groups of data, which is also very very useful. So that is how the whole presentation for today is divided into. You look into what are the general parametric test, sorry, and then you go about what is analysis of variance and how or why you do it. And before closing, we could see if these parametric tests, we can't conduct these parametric tests, how do we go about it, how do we handle with the non-parametric test in our data. Okay, now as we have said, we do hypothesis testing on the population parameters, and when our testing or when our data actually satisfies a certain set of assumptions, okay, a certain set of assumptions, we conduct parametric test. That is, we'll discuss what are the tests, but to summarize or to list out, there are four main parametric tests that we generally consider. One is z test, second is t test, third goes by f test, and the z go last one goes by chi-square test, like chi-square and then f test. These are the four parametric tests that we generally deal with. And the assumptions could be anything, but mostly they are, the samples are supposed to be independent of one another, or we need to get samples from a normal population or something like that. Okay, these are the common ones. There could be anything. It differs from one test to another, or sorry, one distribution to another, but still, what happens is when the assumptions are violated, the results that we are getting are not any more reliable or not very accurate in nature. That is the issue with parametric test. So unless and until you get a reliable surety about your assumptions, satisfaction of your assumptions, we cannot judge or comment upon the validity or accuracy of our test results. Now, the first test is a test. Is a test and t test are two tests that we usually use to test the mean of the data. Now, The most important moments that, as we have discussed or as you might have known, are mean and variance of a data. Okay, so these are the two parameters that we repeatedly come into. Why again? Because any sample you take, what we mean is, like, we know that the sample x bar is actually going to follow a normal distribution with our CLT, as well as we know the sampling distribution is going to of variance is actually going to follow a chi-square distribution. Okay, these are something known to us already. So these are the two important moments that we repeatedly check, like for every data, as to understand the data, as to understand what is the central tendency of the data, as well as what is the spread of the data. These are the two factors that we repeatedly end up checking up. Okay, so the four tests that we discussed today, that we would discuss today, are going to be testing of these parameters, the population mean as well as the population variance. So these are the two parameters that are important to determine, or these are the two parameters of your normal distribution, if you could see, or these are the important factors that are required for us to understand our data more clearly, or to reach into some conclusions. So the first test that we say is actually the Z test. Now, if any one of you could recall, Z is nothing but the standard normal variable, right? So when you say the standard normal variable, whenever for a normal distribution the mean is 0 and the variance is 1, you say that it is following a standard normal distribution, right? Now, to test, if we want to test, if a null hypothesis is to test if mu is equal to mu not being any of the predefined values or the assumed values that we are considering, to test mu equal to mu naught against, this could be any alternative as per our scenario. Okay, it could be either mu less than mu naught, or it could be mu not equal to mu naught, or it could be mu greater than mu naught, mu greater than or equal to mu naught, doesn't matter. So, okay, greater than equal to doesn't work, greater than mu naught. Okay, so your null hypothesis is going to be mu equal to mu naught. You have a single sample, you need to test for the mean of your your testing parameter is mu, that is the population mean. You want to test your null hypothesis, you are defining it as mu is equal to mu naught, if it is some predefined value or not, against an alternative which could be mu greater than mu naught, mu less than mu naught, or mu not equal to mu naught. Now, Z statistic is actually defined as x bar minus mu divided by sigma by root n, where x bar is your sample mean. You obviously know that x bar is something that you use as the proxy for population mean. So x bar minus the mean of x bar. Okay, by CLT you can know that x bar is the sample mean, and it follows a normal distribution with mean mu and where and standard deviation sigma by root n. So to obtain the Z statistic, or the statistic Z is defined as x bar minus mu divided by sigma by root n. That is any of your random variable when it is subtracted by the mean and divided by its own standard deviation, it follows a normal standard normal distribution. That is normal 0 1 distribution. Now, what we do is, if the alternative is mu not equal to mu naught, what we end up doing is, if our test statistic, that is the x bar that you could calculate from your data, is greater than a critical value. If you still remember what was critical value, that is the value corresponding to your significance level, like the type 1 and type 2 error. Alpha was the significance level. So the balancing point of alpha, the point in where you were willing to take the risk, that was called alpha. So the point in where you are willing to take the risk, the corresponding point in your data is called the critical value. Now, if your test statistic value, the sample mean, you obtain the test statistic value from here, if your test statistic value is going to be greater than your critical value, you would end up rejecting your null hypothesis, or you would simply say that you don't have enough evidence to reject your null hypothesis. So when you have a single sample data and you are to calculate, you are to test for the population parameter mu, you could use an Z test if the condition is if you know the sigma value. Okay, it is important. You know that you are testing against a mu, so you would know the value of mu. You know how much samples you have taken, so you can you know n, and you can calculate x bar always from your data, right? So the important point to be known is you need to know the sigma value, you need to know the variance of the data. Only then can you calculate the z statistic, or only then can you calculate your test statistic value. Okay. Now, average lifetime of a bulb, any averages that you want to calculate. Okay. Average time that that is to be taken, any averages that you could come across, or average size of the, what do you say, refill of a pen. In any company you can think of scenarios where you want to test for averages. You could use as a test if you know the variance of the data. Now, what would you do if you don't know the variance of the data? Like, you don't know what is the population variance. The only possible proxy that you could guess is, or you could get is, you could get a sample variance value, right? You could actually get a sample variance from your data. That is the next possible scenario. Now, what, in that case, we use what is called the student's t distribution. Now, to actually apply the t distribution, the assumption goes are the sample is small in size, it is from a normal population, and they are independent. Okay, it follows a student's t distribution, and the statistic stays. If you could actually look into this, is very similar to your result statistic. It simply states t minus mu naught divided by s by root n. Okay, divided by s by root n, because s is your sample variance that you could actually calculate from your data. And what you would do is, you would still do, if your alternative is actually not equal to, you would go for mode t. Okay, reject if mode t is greater than c. uh, if it is greater than is when you use x bar greater than c, and if it is less than, you use generally t less than c. And again, c is similar to what we actually saw first. C is our critical value. Now, your since you are testing for mean, x bar is your statistic, so x bar minus mu naught divided by s by root n is your test statistic. And if this value is supposedly greater than your critical value, then you would reject your null hypothesis. So your null hypothesis could actually go by mu equal to mu naught, or mu less than mu naught, and sorry, null is mu equal to mu naught, and your alternative could be mu not equal to mu naught, mu less than mu naught, or mu greater than mu naught, as per your need. Okay, as per the nature of your data. Okay, so when you know the variance of your population, you use z test, and when you don't know the variance of your data, you use t test. Again, both the z test as well as t test you could use in two sample case also. Okay, average, again, you could think of the same averages that I mentioned above, the examples in the same averages, simply that you don't know the population variance, you apply a t test, sorry, z test. When you know the variance, you do z, and when you don't know, you do a t test. Now consider two sample test, that you want to check the averages of two population. Maybe you have the scores of average marks of students in your class. Okay, you want to know if the average number of girls and boys, okay, is somewhat equal or not. You have a two sample scenario in your hand. When there are two sample scenario also, if you want to test for mean of the data, okay, you want to test mu1 and mu2. If you want to test mu1 equal to mu2, or mu1 not equal to mu2, if the variance is still known, okay, if the variance is known to you, you still use an z test. That just that there is a slight change in your statistic, it would go by x1 bar minus x2 bar. That is a sample average of your girls minus sample average of your boys, minus you assume that both are equal, so mu1 minus mu2 is going to be equal to 0 under h naught, otherwise it should differ, divided by sigma 1 square is going to be the variance of your girls data, or whichever you take as a group 1 data. N1 is the number of samples that you take of the first group, sigma 2 plus sigma 2 square by n2, where sigma and n are the variance and number of samples for the second group of data. Okay, and this would still follow a normal distribution. Okay, this would still follow a standard normal distribution. So when variance is not known, for a two sample case, you use an Z test. Sorry, when variance is known for a two sample case, you use an Z test. Similarly, you could, oh sorry, I guess I forgot, but okay, it is going to be the very similar case. If you are using a two sample case for when variance is unknown, what you could do is, instead of this s sigma 1 square, you could replace it with s1 square. So you would have x1 bar minus x2 bar minus mu1 minus mu2 divided by s1 square by n1 plus root of s1 square by n1 plus s2 square by n2. It will follow t distribution with n1 plus n2 minus 2 degrees of freedom. Okay, but you could think of the same example scenario where you will have two averages to check into. You need you are checking the equality of two averages, but the variance is unknown to you, and s1 square and s2 square will correspondingly be the sample variances of your first group and the second group. Okay, so to test the mean, you have two tests in your hand, two parametric tests in your hand, z test and t test. Just keep in mind that z test is used on the basis of the standard normal distribution. It is used when you have an idea of the population variance, and if you have no idea about your population variance, you use a t test. Both of these could be applied in one sample scenario as well as in two sample scenario, and both of these tests are used to test the population mean of your data. Any doubts or any examples that you want to clarify before we look into the variance part? No doubt. Okay, maybe at the end you can think of some examples and tell us what are the scenarios that you could put into two categories. Okay, so now comes the test of variance. In test of variance also, we have two tests. One is chi-square test and the other is f test. Now all these things that we are stating up, is it standard normal, as you know, is a distribution. Studency, as you know, is a distribution with the definite moments, with definite PDF and all, as you have seen for all the standard distributions. I'm not boring you with that, but then, yeah, you have a definite formula for it, and you also have all those calculated tables. Just like the standard normal tables, you also have all those calculated T tables, Z tables, and all those things that are required, and you could actually calculate it values of it, which is why it is much simpler to handle the parametric test, that you have all calculated values of probabilities for probably mostly all the available degrees of freedom in your tables, done with you, okay, or in hand or handy. That is why we generally prefer parametric test. Now the chi-square distribution, it is actually test. Chi-square is, even though there is a distribution named after chi-square, we use it to test a variety of substance. Even though sample variance is one most important test that is considered and is considered as the parametric test, you could also check for homogeneity of variance or goodness of fit test. Okay, what it is, I'll tell you. Sample variances, as the mean case, you are testing if sigma square is equal to sigma naught square. That is a single sample case. You want to test if your sample variance, the population variance, is equal to some particular value. Okay, a particular value. If the variance of the data is, say, 3 or 10 or whatever it is, okay, you want to check if it is an exact value. That is what happens with testing of variance. Now the second thing is goodness of it. Goodness of it is nothing but, you want to test if your data, you are assuming that your data is following, say, Poisson distribution. You want to actually test if it's valid to fit a Poisson distribution into your data or not. Okay, to test if your fitting of, or you choosing the Poisson is actually an ideal way or not. Okay, that is goodness of it. The third goes for homogeneity of variance. You do that mostly when you have you have more than one group of population with you, and you're taking sample from each case, and you want to test if each of the category that you have in your population is of is having a same variance within it. Okay, if the variances between the categories are equal or not. And the last is check of independence, whether your variables you could make a 2 by 2 contingency table and you are checking if the variables are independent or not. Okay, these are the general test or the most widely used test that you could of chi-square statistic. And in case of chi-square test for variance that we look into, you are testing if h naught sigma is equal to sigma naught, a particular value. Okay, sigma is equal to sigma naught against any alternative. Again, this could be sigma greater than sigma naught, sigma less than sigma naught, and sigma not equal to sigma naught. And the sample variance s square is what is denoted here. N minus 1 s square by sigma naught square is actually following a chi-square distribution with n minus 1 degrees of freedom. That is how you end up checking for a that is how you end up using a chi-square test, or it is what it is named after. And sorry, again, you would actually check if it's a sigma greater than sigma naught, you will have the criteria as s greater than c. Okay, so anyhow, whatever is your rejection criteria, this is called the rejection criteria. This would depend upon what is the sign of your alternative. Okay, now s greater than c, again c is going to be a critical value. You would simply say if your test statistic value is greater than the critical value. That is a common rule. Okay, for any parametric test, your common rule is going to be if your test statistic is greater than your critical value, you end up rejecting your null hypothesis, or greater than or less than. The inequality will depend upon the sign of your alternative. So based upon that, you would say if your null hypothesis is rejected or it is not rejected. Okay, so the chi-square test of variance would make us calculate the statistic as n minus 1 s square by sigma naught square, where sigma naught square is your assumed value and s square is going to be your sample variance. And now what will you do if you have two samples of chi-square? Okay, you want, sorry, you two samples and you want to test for variances of the two sample set that you have. Okay, you simply want to know, you have calculated two sets, you have actually observed two set of samples, and you could just by looking you could see that the central tendency values are almost same. Okay, but you want to know if it's still from the same population. The next quality check that you would put into in place is to check if the variances of both the data are similar or not, right, are equal or not. Now to test that, what you use is called the f distribution. So in one sample case you use chi-square in terms of variance, and when you have two sample you use f distribution. Okay, now f is again a distribution named after Steneker, and the statistic that you would calculate is sx square by sy square, where sx square is the sample variance of your first sample, and sy square would actually go by the sample variance of your second sample. Now because uh, f is not really what do you say, not a symmetric distribution per se, you could have a right tail critical value as well as the left tail critical value. Okay, whatever you observed, z and t were symmetrical in nature, so it doesn't matter, the critical value is going to remain the same. And for chi-square you have only tables onto your right and tail. So but for f test you could have two critical values, that is you could find a critical region on this point as well as you could find a critical region on this point. And the c values, unlike in z and t cases, the c values, the critical values, that is a probability containing upon this point afterwards and this point afterwards, are going to be same. Even from the graph you can see, to contain a 0.5 probability, maybe you need this much on this side, but on this side you need a very small interval, right? You might not need that much because there is height over here. So because of that, the critical values, the right hand critical value as well as the left hand critical value, are going to be different. So to test the same thing, when you have a not equal to scenario, you will have two critical regions. Like both the cases, actually every cases you have two critical regions, but the c values are going to be same if they are symmetrical. But since f is not symmetrical, you could have you reject it if it is anyway greater than your critical value or less than. If it's on the left hand side, like on this side, you say if it is less than your critical value, you reject it. If it's on this side, you say if it's greater than your critical value, you would reject it. Okay, so that is it. Importantly, The parametric tests that you do are to test for the population parameters. The important, okay, before winding up, why parametric test? It actually, since the all the probability values are calculated, and these follow a standard PDFs, and you could actually precisely calculate the values if you are able to have these assumptions satisfied. You get proper like accurate results, okay, better reliable and accurate results. That is the advantage of a parametric test. And comparatively to the non-parametric scenario, you have very less requirement of data, okay. But at the same time, if there is a slight variation in any of your assumption, and it is no longer any of your even if one is violated, the test becomes completely unreliable, okay. So unless you get a proper assumption satisfied, you cannot proceed with parametric test. In real life, what happens is, not all time can you get your assumption satisfied. Maybe normal and all you can even try by collecting a bit more samples, or doing some basic transformations like log or something. But not always is it possible to do that, okay. That is one of the biggest drawback of your parametric test, okay. Which is why we we are in need to actually move into a non-parametric scenario. Also, before actually moving it to non-parametric, you need to know how to analyze the variance, which will be handled by Shavna. Just before that, a quick rewind. You have four parametric tests in general. One is the Z test, where you test for mean, which could be done for one sample as well as two sample. The only thing is, the variance should be known. Only in that case could you use an Z test. The second part goes by T test, where you again test for mean in as well as one sample and two sample case, but it is applied when variance is unknown to you. And in case of variance, to test the population variance, you have to test chi-square and F. Chi-square test is used if you have a single sample, and F test is used when you want to know, when you are comparing the equality of variances of two different samples, okay. So before winding up and moving on to Shabna, she'll handle what is analysis of variance when you have more than one or two groups, okay. What would you do then? Hi, thank you. Do you have any doubts? Sorry. Any questions? Thank you.
Well presented, Shukarna. We got a revision of stats too, especially. Hi, I am Shravana. Good evening, everyone. Today I am going to explain a fundamental statistical tool analysis called ANOVA, which stands for Analysis of Variance. Okay, let me share the screen. So here I will be explaining the basic concepts of ANOVA with the help of some relevant example. Here I shall talk about what is ANOVA, different types of ANOVA, and some practical examples to explain this concept better. What is ANOVA? ANOVA stands for Analysis of Variance. It is developed by Ronald Fisher. ANOVA helps us to test the significance of the difference among more than two sample means. It is basically an extension of the t-test and allow us to move beyond just comparing two population means. When we have two samples, p-test and ANOVA will give you the same results. However, using t-test would not able to be reliable when there is more than two samples if we conduct multiple t-tests for comparing more than two samples. It will have a compounding effect, right, on the error, which will lead to a type 1 error for each t-test. This is why ANOVA is important over t-test. So ANOVA is basically of two types, one-way ANOVA and two-way ANOVA. One-way ANOVA is, what is the difference between one-way ANOVA and two-way ANOVA? One-way ANOVA holds, when we talk about one-way ANOVA, it has one factor of independent variables and compares three or more levels of one factor. whereas two-way ANOVA is an extension of one-way ANOVA, which compares the effect of multiple levels of two factors, and it holds more than one factor of independent variables. So, the, here we know that t test for ANOVA is what is the f test. Coming to the assumptions of ANOVA, the population from where sample is taken must follow a normal distribution. It is strictly. And next, the sample selected randomly and independently, and each group should have a common variance, and datas are independent. I know it's going complex. We will get to know more about ANOVA by solving examples that will give you a clear view of this topic. First, basic things of ANOVA. Null hypothesis. In null hypothesis, under ANOVA, we hold that mean for all groups, in the sense all samples are same. Null hypothesis on ANOVA says that H naught says that mu1 equals to mu2 equals to mu3, and that of alternate hypothesis it states that it will be at different there will be different mean for at least one pair of groups, that is m1 might not equals to the rest of the groups. Okay, now ANOVA is especially a F distribution, as I've told you. ANOVA is determined by the variance between and variance divided by variance within. What is this? Now let us know what is the difference between variance between and variance within. So let us consider this three samples: sample 1 with mean x1, sample 2 with mean x2, and sample 3 with mean x3. Now, what is variability around or within the distribution? Just a minute. 1 minute. Sorry for the disturbance. I'm continuing it. So here I was in. Hmm. So let us see what is the difference between variance between and variance within. We have compared three samples with the sample means x1, x2 and x3 to see if there is any difference amongst them. So the question is whether they are coming from the same population or not, or one mean is slightly offset from another other two, right? So the variance around or variance within distribution is the internal spread of the variance of each distribution, like this. And this is the variance within, and or variance around. Will take again, there are three means mu1, mu2 and mu3, and plotted, these are plotted, and the ability plotted for ability among number between plot the and we plot the normal distribution curve to see what is the uh, distance of each mean from the overall mean here. So in this case, a null hypothesis would be mu1 is equal to mu2 equal to mu3, whereas the alternative hypothesis will be mu1 not equals to mu2 not equals to mu3. So this is how we calculate the variance along and variance between. And ANOVA is basically the ratio of these two. Now, total variance is actually the variance between plus sum of variance between and variance between. Now, if the ratio of these two is greater than 1, if it is greater than 1, we reject the null hypothesis. If the ratio is less than 1, we fail to reject the hypothesis. And similarly, if it is equal to 1, we fail to reject the null hypothesis. So, let us know it by an example. We want to see if there is different studying methods can lead to different mean exam score or not. To test it, we select 30 students and randomly assign 10 students to use a different studying method. We will solve this using two different methods. Let me look into method 1. Here I have listed the three different methods: method A, method B, and method C. Now, their grouped mean is given. The method group mean of method A is 8.7, group mean of method B is 8.6, group mean of method C is 8.5, and the overall mean of this thing we get 8. Here will be a 1 point. Overall mean 8.6. We have now we calculate the variance between is 10 for the number of observation. 8.7 is the group mean of method A and minus 8.6 is the overall mean whole square. Similarly 10, 8.6 minus 8.6, here 8.6 is the group mean for method B and 8.6 is the overall mean. Similarly for method C, it's 8.5 the group mean and overall mean is 8.6. So we got the calculation is 0.2. Keep it aside. Now for group within variation. So here for method E, for we calculate variation for its observation. For method A, we calculate variation 10 minus 8.7, that is group mean, whole square. 9 minus 8.7. We know this method, right? I'm not going to elaborate it. For each observation, actually, we are doing this work for method A, method B, and method C. We found the variance. We sum it and we get the variance within. Now, earlier we said that ANOVA is the ratio of variance between and variance within. We have got variance between is 0.2 and variance within is 28. Now 0.2 and 28 is 0 point something. And if the ratio is less than 1, we fail to reject hypothesis. This means that the means are very close to the overall mean and the distribution overlap is hard to distinguish. Now let us try to solve this in another method using the F test. Now the thing need to know this: if F critical is greater than F stat, we fail to reject the null hypothesis, and if it is lesser than F stat, then we reject hypothesis, null hypothesis. How? Consider that earlier example. Now we assume alpha equals to 0.5. Now f stat is actually we have counted earlier 0.0071, and that is the ratio of variance between and variance within, and f critical is the numerator. How is f critical is calculated is the number of samples. We already have three samples: method A, method B, and method C. That is 3 minus 1, number of samples minus 1 goes in the numerator part, and for the denominator part we see that here is 30 observation, 10, 10, 10 for each, minus number of samples, that is 3. So 30 minus 3, 27. So f critical, how we will found f critical? F critical is 2 comma 27. For df1 we will locate column number 2, okay, and for df2, under df2 we will look at column number 27. Here you will get a f table. and the intersection of both the boxes will give you the value. F critical is we are getting 3.35. This is actually less than, this is we can say that F critical is greater than F sat we have got. So we fail to reject the null hypothesis. So in both the test cases, we come to a conclusion that here also by using t-test, we fail to reject the null hypothesis, and similarly by f-test also we fail to reject the null hypothesis. So today we learned about ANOVA. I just covered a brief part uh, about what is ANOVA, the most important powerful statistical tool for comparing multiple mean groups. We explored two types, that is one way and two way ANOVA. We knew about the assumptions. We got to know about, we understood the importance of F test, the concept of variance between and within groups, and how ANOVA helps in hypothesis testing. That's it from my part. Now, if you have any doubts or any, if you have anything to say, you can write it in the message box. This That's it from my part. Now I shall hand over to Shama Broto.
Okay, nice. Very nice presentation by the Ravana. She just explained one way ANOVA and two way ANOVA, one observation parcel. Though we have a scope to discuss about M observation parcel, we'll do that laterly. Is my screen visible, guys? Okay. So first we should be now we should be discussing non-parametric test. Okay. So any of you, can you tell me what is we are referring here by saying non-parametric? Anyone, please? Um, I guess it has been discussed earlier, so we should be able to answer. Uh, Anyone? Harsh, Arijit, anyone? Okay. Let us know what is for which distribution is not known. Yeah, fair enough. So basically, in this scenario, we'll be dealing with those testing problems where we don't have that much information about the parent distribution. So by distribution, we always refer to the parent distribution. This approach is also known as distribution-free approach. Uh, Now, why so? The distribution-free approach is basically referring that we don't have any specific distributional assumption. That doesn't mean we don't have any parent distribution. We have a parent distribution, we have a valid parent distribution from which we have drawn the samples, but we don't have enough data to say the parent distribution was following normal or exponential or Laplace. We can't say what was the exact distribution function. We don't know the parameters, we don't even know the distributional function or CDF of the parent distribution. So that's why we don't have any distributional assumption. So as we don't have any distributional assumption, we have to work without the help of the theoretical distributions which we are already known of, right? That's why this is the computational method is totally free from any distributional assumption. That's why it's called distribution free approach. Now, what do we mean by no assumption? Why can't we do any assumption? Because we don't have any enough data so that we can tell this is coming from normal or this is coming from exponential or this is coming from beta. Okay, so this is basically lack of data, which is leading me towards non-parametric hypothesis testing instead of parametric hypothesis testing. So we should always admit this. As we are having no enough data, that's why we are switching to non-parametric. So parametric tests are always efficient than non-parametric cases. Whenever we are compromising with data, we have to choose non-parametric scenario. Otherwise, we'll always go for parametric scenario first. Now, what do the parameter signifies? So we have already seen that parameter is nothing but the characteristics of the parent distribution. Now, this parent distribution is defined by the distribution function. When we don't even know what is the distribution function, what gonna be my parameter over here? So this in this scenario, the parameters are referring the index of the family of distribution or the uh, index of family of distribution of parent distribution, not the characteristics of the parent distribution. And in statistic, is there any real existence of no assumption? Is it really possible? It's gonna be so complicated. We don't if we don't take any assumption. So is it actually giving me the same sense as no assumption? No, it is not. So here also we have an assumption that the parent distribution is an absolutely continuous distribution, or the random variable which is following the parent distribution is absolutely continuous random variable. Okay, any doubt? Okay, next. So let us look uh, towards few non-parametric tests. Like first, we're going to look into one sample location problem. Okay, so location, how location is being denoted? We have few characteristics, location characteristics. In parametric scenario, we had mean, right? But if we are not aware of the distribution function, we can't calculate mean. But one thing we can calculate, that is median. Median is always distribution fee, right? So if we are trying to estimate or making assumption towards median, it will give me um, some data about the location of the distribution curve. Okay, so in one sample problem, we'll try to make some inference regarding the location of a distribution. First thing which we're gonna do is sign test. Okay, how sign test works? Uh, in this scenario, basically we are taking an assumption in null hypothesis that our parameter, which is median, is taking a particular value. Okay, and we can have three different alternative hypotheses. First one is uh, right tail right tail test. You guys are always already aware of. And second one is left tail test, and third one is both tail test. So what does this mean? What it is signifying? I gonna check if the actual value of the median is lying on the right side of the assumed value. This is gonna be our first alternative hypothesis. The vice versa gonna be our second alternative hypothesis. We're gonna check if the actual parameter value is lying on the left side of the assumed value, and uh, on the third alternative hypothesis, we are combining the first two. We're gonna check if it is just not equal to the assumed value. The parameter is not equal to the assumed value, so it can lie in the right, it can lie in the left as well. So it will lead me to a both tail test. In this scenario, what we'll be doing, we'll just check, we'll just define a random variable zi. Okay. For each observation, I'll be getting a binary output. If that observation which is equal to, which is greater than the assumed median value, I gonna get a 1, otherwise I'll get a 0. So I'll get 1 for each observation which are greater than the assumed median value and 0 otherwise. Okay. So we're gonna get n number of ones if there are n observations which are greater than the assumed median value. Okay. So now we are defining our test statistic, uh, which is S, right? So S, what is S? S is the sum of Zi's. So basically S is a random variable which signifies the number of observations which are greater than the assumed median value, and median value should be the middlemost value. So why we are doing so? We should get equal number of 0 and equal number of 1 at the end of the transformation if the h naught is true, right? If the h naught is true, we should get equal number of observations, right? That means S should follow binomial distribution with n comma half. Why half? Because we have equal chances of getting a 1 or a 0, right? So ultimately we are coming to any distribution only to get the probability. And based on this, I'll be finding out the probability that theta naught, theta is becoming theta naught. Theta naught is the assumed value of theta. Now, if that comes with a significant level, significant alpha, then I gonna say that yeah, we don't have enough proof to discard null hypothesis. So the assumed value of theta is actually true, and otherwise we have to discard the null hypothesis and choose the appropriate alternative one. And in this scenario, we have three alternatives. And for that, we can get three different test criteria. Okay. Like here I have signified if S is becoming like mm, lesser than C1, C1 be the critical value. And in the second scenario, S will becoming more than C2, C2 be the critical value. And both tail test, in both tail test, we're gonna have a both bound upper and lower boundary of S. Okay. So basically, I'm trying to make an inference on the location of the distribution we have, although we don't have any knowledge about the parent distribution. Fair enough? Any doubt, guys? Any doubt? Or should we go forward? Okay. Uh, okay. Yes. Now we're gonna check for two sample location problem, like paired sign test. What is paired sign test? In this scenario, we're just gonna compare between two groups, just like we did in pair t-test, right? In the case of pair t-test, we are comparing two means, right? You are checking for equality among means of two different groups. In this scenario, our old parameter is constant, that is median. Median for the first group, we are assuming that median is theta x and the second one is theta y. Okay. And we gonna check for if theta x is equal to theta y. So our null hypothesis gonna be theta x is equal to theta y. We can take a different random variable theta z, which gonna be the difference of theta x and theta y. So theta z should be 0 if null hypothesis is true. And we can test three cases, right tail, left tail, and both tail test. If theta x is greater than y, theta x is less than y, and theta s is not equal to y. Fair enough? So basically, we are comparing between medians of two different groups, and we should keep this in our mind. The subgroups or the groups we are comparing should be of equal length. So the sample drawn from the first group should be number of samples drawn from the first group should be equal to the number of samples drawn from the second group. Otherwise, it's gonna lead to a issue which can't be handled by pure sign test. We have other tests to handle that, but in this scenario, what we are doing, we are just doing this. Okay. Now let us calculate Z1, Zi. Zi, what is Zi? Zi be the random variable where Zi is denoting the difference between xi and yi. So it will take the deviation between ith observation of x and ith observation of y. So it could come uh, in negative if yi, the y ith observation of y is greater than ith observation of x. It will come positive if it is what? It is greater than xi is greater than yi. So again, this simplifies into one sample problem. Zi is now transformed into ci, where ci is 1 if zi is greater than 0 and 0 otherwise. Okay, understood? Now, similarly, s gonna be the number of sum of zi's where sorry number of ci's where s will be following binomial n comma half under null hypothesis. Same problem, we're gonna check if it is following or not, validating or not. Okay, I guess cool enough. Any question regarding this problem, two sample location problem? Okay, next. Now, what we gonna do? We got till now what we were checking like median, right? But this time we gonna check if two distribution functions are similar to each other or not. Okay, not only in terms of median, in terms of shape, in terms of distribution function. If we don't know the structure of the distribution function, but we will check if both the structure are similar to each other or not. Okay, so basically this problem is called Mann-Whitney U test. Okay, which is similar to Wilcoxon rank sum test. Okay, not Wilcoxon run test. This is Wilcoxon run sum test. In this scenario, what we are trying to do, we are trying to find if a distribution function is stochastically larger than a different distribution function. Suppose we have a random variable x and we have a different random variable y. We're gonna check if the random variable x is stochastically larger than random variable y, which is simplified here like if the distribution function for a particular value z is giving a higher value for x than y, it signifies that the prior random variable is stochastically larger than the later one. Stochastically larger means a random variable will have a location which is more than the variable. Okay. Is it understandable or should I go a little deeper? Like, should I talk about stochastically larger a little bit or is it understandable? Basically, the whole thing, whole distribution is shifted towards left or right is being judged by the statement stochastically larger or stochastically smaller. Okay, understandable? Okay, please elaborate a little bit. Thank you. Uh, Basically, as in the diagram we have mentioned, see, y is occurring earlier, right? The probability of y in the plot is occurring earlier. The peak of the y is coming earlier than peak of the x, right? Okay. So the most of the probability mass is larger in the larger area in x than y. Is it understandable now? Like the mass, the amount of mass being is lying in larger section or in more positive section for x than y. The most mass of y is lying around 0, right? In the graph I have mentioned. But if in case of x, the amount of mass or the density is getting concentrated around 2. So the most mass is getting concentrated for x for a larger value than y. This signifies that x is stochastically larger than y. I guess it's helping, right? Okay. Let us proceed. If you want to know a little bit more about stochastically larger, how the notion arrived, why stochastically, and the word stochastically, what it is signifying, then we can talk about it in the group as well. Okay, laterally. Now, in this scenario, what I gonna do? I gonna check if both the distribution functions are equal, right? So this is basically testing for similarity. And this is basically testing for similarity of the distribution functions, right? And H1 gonna be X1 is stochastically larger than sorry, random variable X is stochastically larger than random variable Y for all Z, for all the points. Okay. For this, what we gonna do? We gonna do the same thing if um, if x1 ith observation of x is greater than y ith observation of y, then I gonna take a 1 and otherwise 0 and laterally I gonna sum them up. Okay. Now that is our test statistic u. If that value is that value is giving me a giving me a hard comparison to the critical value C or hard comparison, then we have enough evidence to reject H naught. Okay, then we have to say that null hypothesis is being rejected. Otherwise, we won't be having the evidence to reject H naught. Okay. Similar to other test, but I'm deriving the notions or setting up the scenario in a little bit format. Okay. Now, the most important one, that is multiple group station similarity problem. Earlier, we are checking similarity between two groups, right? It's just like ANOVA, what we did, but normality assumption are not being taken. Okay. In this scenario, we are setting up a null hypothesis that we have, I guess, C number of random variables, and all the random variables are taking same distribution function. Okay. And alternative could be anything like bleaching. Even a single equality will confirm the null hypothesis, sorry, alternative hypothesis. So here our test statistics be Ri, or sorry, H, where this test is also popularly known as H test. Okay, where we are calculating stuff on Ri. Ri be the observed value of rank sum. So basically, what we are doing, we are firstly ranking them up, ascending order or descending order, and then summing the rank according to the need. So basically, we are combining both the samples and ranking them up, then distributing it, and then adding the ranks of each observation from both the groups, all the groups. Okay. And based on that rank, we are taking a ratio and summing them to form our statistics. Okay. Why we are forming it in such a way, such a complicated way? 12 by n into n plus 1, why so? Because under the assumption of H naught is true, this test statistic will asymptotically follow chi-square distribution with degree of freedom C minus 1, which is the uh, number of samples or the number of groups we have, sorry, number of groups we have, right? So we can perform this test as well for two groups, what we did earlier in case of Mann-Whitney test. But in that scenario, this test statistic will follow chi-square with degree of freedom 1, which is basically summation of standard normal square of standard normal variates. Okay. And we all already seen that here we are getting standard normal variates only. Okay. Now we can compare the obtained value from the chi-square table, which is tabulated value, and based on that comparison, okay, based on that comparison, we can perform, we can take our decision, right? But there's a constraint. This asymptotic distribution will not fit properly for smaller value of C. So if we have less number of groups to compare, then we can't come to the decision that it is following chi-square distribution asymptotically. So for a larger group numbers, we can draw the inference. Okay. There are few more non-parametric tests like run test for randomness, world tool fit test, Friedman test, and etc. etc. Due to time constraint, uh, we are not able to discuss all of those things. So these four tests we thought that gonna be important for you guys and for us as well. So we discussed. If you guys have any question regarding these four tests or anything we discussed today or anything we haven't discussed today or anything regarding our club or events, you can ask. Any feedback?
Um,
You guys have any doubt?
Arjun got something to say, I guess. He just said, I
Yeah,
have a request.
yeah, yeah.
No.
Hello,
Yeah.
am I audible?
Yeah, you're
So
right.
I have a request here. Actually,
Uh,
we are preparing for final exam, na? So can you
hmm.
please once more repeat this one after the final exam, and can you please share these
This
slides with us?
this link will be the meeting link. Sorry,
Okay,
video will be available in YouTube. You can
okay,
rewatch
okay,
anytime. or
Okay.
if there's a good number of requests to repeat, we will
Okay.
surely repeat this.
Okay. 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 Because
Hmm.
these are very important tests actually. So we'll have
Uh,
to study. That's why I'm
yeah,
asking.
if you need, I can provide the study material
Okay.
in
Okay. Okay.
the group as well.
Okay. Okay. Please. Please do that.
Okay,
It will be
thank you.
helpful. Okay. Thanks.
Okay, yeah, Sukanya. Sukanya?
Yeah, no, no, I was just saying he had something to say. He had this message. That's it.
Okay, okay. So that's it, guys. That's it for today. See you on the next event. Yeah,
Sure.
Thank you,
Thanks. Okay.
everyone.
goodbye.
Thank you.
Yeah.
Thanks for
Okay.
joining, guys.
Thank you.